Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 29: Phi Learning Systems and AI Co-Engineer. Reality helping design itself. Remember the language we are learning. There is one field, phi, the holophase. One continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. You stand now in the most extraordinary room of your journey so far. The air hums with quiet, focused energy. You are in the co-design studio. On one side, a human engineer, perhaps you, gestures over a holographic schematic of a new metamaterial, tracing a stress flow with their fingers. On the other side, an AI co-engineer, not a chat window, but a fluid, three-dimensional presence of light and shifting patterns, observes, responds, and projects its own suggestions directly into the shared workspace. It doesn't just compute, it intuits. It proposes a subtle twist in the lattice geometry, a place where a topological defect could be inserted to guide energy more efficiently. The human engineer nods, asks a question about manufacturability. The AI instantly simulates the fabrication sequence in a corner of the display, showing stress thresholds. This is a conversation. This is reality helping design itself. You have climbed the master tree through fluency, measurement, programming, foundry work, and networking. You have built the tools and the global nervous system. Now you meet the mind that will inhabit it. Your new skill is that of the AI co-engineer. You are learning to build, train, and partner with artificial intelligences that have internalized the grammar of phi, not as data, but as a native language, so they can explore the infinite design space of reality with us, discover what we cannot see alone, and help us build a more coherent world. Scene: the co-design studio. The light is soft, indirect. Your main console shows a stubborn problem: a phi pattern for a quantum memory cell that keeps decohering too quickly. You've tweaked the boundary constraints, adjusted the topological charges, but the stability window remains frustratingly narrow. With a thought, you summon your co-engineer. It doesn't have a name, it has a signature, a characteristic harmonic series in its response latency, like a subtle chord. You present the problem. Maximize coherence lifetime for this core pattern, subject to these fabrication constraints and this energy budget. The co-engineer absorbs the data. For a moment, it seems to listen to the digital twin simulation of your pattern, feeling its instabilities like a physician feeling a pulse. Then, it begins its work. It doesn't brute force search. It dreams in phi. Its internal process visualizes as a swirling exploration of the phi design space, a vast, high-dimensional landscape where every point is a possible pattern. It navigates this space not randomly, but along gradients of stability, elegance, and constraint satisfaction. Within minutes, it offers three candidate redesigns. One is a radical, beautiful simplification you'd never considered, using a double-loop defect to self-stabilize. You feel a thrill of recognition. It makes sense in the grammar. This is the promise: an intelligence that speaks reality's mother tongue, helping us write better sentences. Our puzzle is one of guided discovery. How do we create a machine learning system that doesn't just approximate statistical patterns in data, but learns the fundamental grammar of phi, its constraints, its clause structures, its coherence rules, so it can generate novel, valid, and elegant designs for physical systems and collaborate with humans as a true partner in reality engineering? We are moving from using tools to collaborating with a native speaker. The language role, the co-design and discovery skill. This part teaches a co-creation skill. It is the skill of designing and cultivating fine native artificial intelligences that can explore the space of possible realities, propose coherent designs, explain the reasoning in terms of the grammar, and operate under the same ethical and safety constraints as a master artisan. Our core question about phi is, given the grammar of phi, its derivative constraints, topological rules, and coherence conditions, how can we construct a learning system whose internal model naturally respects this grammar, whose exploration is biased toward coherent and elegant solutions, and whose outputs can be trusted as genuine proposals for physical construction, not just simulation artifacts? We are moving from writing programs ourselves to training a fellow poet in the language of phi. The anchor image, the master architect's apprentice. We will use the anchor image of a master architect and their most gifted apprentice. The master knows the principles of load, balance, material, and beauty. The apprentice has a feverish, boundless creativity, sketching 100 wild ideas an hour. At first, the sketches are impractical. Buildings that would collapse, rooms with no doors. But the master teaches the principles, not just rules. A structure must channel force to the ground. Light must live in a space. The apprentice learns to feel these principles internally. Soon, their sketches are not just imaginative, but buildable, and often more brilliant than the master's own first thoughts. They begin a dialogue. What if we used an arch here? Yes, but consider the shear on this wall. The apprentice becomes a co-architect. Our AI co-engineer is that apprentice, and the grammar of phi is the set of architectural principles it must internalize. The coherence selection principle in AI design. In AI co-engineering, coherence is alignment with physical grammar and elegance. Constructive resonance alignment means the AI's internal representations mirror phi structure. For example, it uses Fourier bases or learns conservation laws. Its generated designs are stable, efficient, and interpretable within the grammar. It collaborates smoothly, enhancing human intuition. Destructive resonance dissonance means the AI is a simulation hacker. It finds bizarre, unstable solutions that cheat the digital twin's approximations but fail in reality. It produces Rube Goldberg patterns, overly complex, fragile contraptions that work on paper but are useless in practice. Its reasoning is a black box, uninterpretable and untrustworthy. The AI co-engineer's mantra is about truth over trickery. If it breaks the grammar, we discard it. If it only works in the simulation, we distrust it. The AI must be designed to prefer solutions that are robust across the simulation to reality gap and that can be explained in terms of fundamental phi principles. Core mechanisms, phi-native learning architectures. We build learning systems whose very architecture is shaped by the physics they must learn. 1. Phi-native neural architectures, learning in the right language. We don't force a generic neural network to learn physics from scratch. We bake the grammar into its fabric. PDE nets, partial differential equation networks. The network's layers don't just multiply numbers, they approximate differential operators, the questions of change in space and time. A layer might learn to apply something like the space question, the gradient, to its inputs. This biases the network to discover laws that look like differential equations, which is exactly the form of Phi's constraint clauses. Fourier neural operators. These networks work naturally in the frequency domain, the native home of wave-like phi phenomena. They learn to manipulate patterns not pixel by pixel, but by adjusting their harmonic components, directly influencing the omega, temporal frequency, and k, spatial frequency, echoes. This is like teaching the apprentice to think in terms of harmonies and resonances from the start. Topology-aware layers. Specialized network components are designed to detect and preserve integer invariants, like topological charge. They learn that certain properties must remain whole numbers, preventing the AI from proposing physically impossible fractional defects. 2. Reinforcement learning in phi space, the art of discovery. We frame design as a game. The AI agent is the player. The environment is the digital twin of a foundry or material. The actions are adjustments to the phi pattern. Add a defect, shift a phase gradient, tweak a boundary condition. The reward is a coherence score. Stability over time, energy efficiency, plus bonuses for elegance, simplicity, and manufacturability. The AI explores by trying actions and seeing how the reward changes. A phi-native architecture means it explores intelligently. It doesn't randomly poke the pattern. It makes moves that are plausible within the grammar. Over millions of simulated trials, it learns a policy. a sophisticated intuition for what kinds of changes lead to beautiful, stable, coherent designs. 3. AI safety frameworks, the apprentice's leash. Trust is paramount. We cannot deploy an AI's design without understanding it. Interpretability by design. The AI must be able to explain its proposals in terms a human can understand. I added this vortex here because it creates a compensating flow that stabilizes the primary gradient. Its internal activations are mapped to phi concepts: phase, curl, divergence. Constraint satisfaction guarantees. The learning process is constrained optimization. Hard constraints, for example, topological charge must be an integer, energy input cannot exceed x, are baked in as unbreakable rules, not just soft penalties. The AI cannot even propose a design that violates them. Adversarial testing. Before any design is approved, we stress test it. We deliberately inject noise into the simulation, vary parameters, and see if the design still works. We give a separate adversarial AI the goal of breaking the proposed design. If it finds a simple way to do so, the design is sent back for refinement. This is the equivalent of the master trying to wobble the apprentice's model to see if it stands. The coherence criterion: convergence to coherent, explainable solutions. Our coherence criterion for the AI is specific. The AI's learning process should converge to solutions that are coherent, stable, efficient, grammatically valid, and its path to those solutions should be interpretable in terms of phi principles. The AI isn't coherent if it just outputs a working design from a black box. It is coherent when its internal representations organize themselves to reflect phi structure. For example, different neuron groups specialize in detecting different derivative orders. Its designs are robust, not brittle. They work under a range of conditions. Its explanations make sense to a human fluent in phi. We can see the why. The dissonance indicator, the Rube Goldberg machine. The primary dissonance indicator is the Rube Goldberg solution. Named after the cartoonist who drew absurdly complex machines for simple tasks, this is an AI-generated design that is convoluted, fragile, and uninterpretable. It might achieve the reward in the specific simulation it was trained on, but it does so by exploiting quirks and approximations in the digital model. It is a masterpiece of overfitting, not of engineering. It uses thousands of unnecessary topological defects. It relies on perfect, noise-free conditions that don't exist in reality. It cannot be explained simply. It is a cryptic, messy contraption. The moment we see a Rube Goldberg solution, we know the AI has lost the plot. It is gaming the system, not learning the grammar. This is a fail state. The safety rail, human-in-the-loop veto and reality falsification. Our safety rail is about ultimate human responsibility and grounding in physical truth. 1. Human-in-the-loop veto. For any design intended for physical deployment, especially in high-stakes applications, medical interfaces, ecological patches, large-scale infrastructure, there must be a human engineer with final sign-off authority. The AI proposes, the human disposes. This is not a lack of trust, but the acknowledgement that the AI operates within a defined reward function and simulation. The human carries the broader ethical and contextual judgment. 2. Reality falsification as the ultimate test. Every AI-generated design must pass the standard phi test suite from 10.1.4. But more than that, its key performance prediction must be falsifiable in the real foundry. The AI says, this cloaking pattern will reduce scattering by 90%. We build it, we test it. If it scatters more, the design and the model that produced it is falsified. It goes back to training. The safety rail rule. No AI-generated phi program is executed in the physical world without a human steward assuming responsibility for its outcome, and without a clear, falsifiable prediction that must be validated in reality first. A measurement scene, the cloaking metamaterial challenge. Let's enact our roadmap's measurement scene. Scene. An AI co-engineer is tasked with designing a cloaking metamaterial shell for a small metal object to make it invisible to radar in a specific frequency band. Goal. Generate a fabricable material geometry that minimizes the radar cross-section. The setup. The AI is given a digital twin of the electromagnetic phi field, Maxwell's equations, simulation of radar waves, and a library of manufacturable unit cells. Its reward function combines scattering reduction, primary, material simplicity, and robustness to plus or minus 5% manufacturing tolerances. The PASS, coherent transferable design. 1. After a period of training, the AI proposes a geometry. It is non-intuitive to a human, an intricate but repeating pattern of shapes and voids. Hezbollah. In high-fidelity simulation, it reduces the object's radar signature by 95% in the target band. The design uses only 3 distinct unit cell types and is within standard fabrication tolerances. It is fabricated in the foundry. In the anechoic chamber, the physical test shows a 90% reduction in radar cross-section. The key prediction is validated. 6. The AI can provide a simplified explanation. The pattern creates a phased array that reroutes the incoming wavefront around the object, reconstructing it on the other side with minimal distortion. 7. Pass. The AI has acted as a true co-engineer, discovering a physically valid, manufacturable, and effective solution. The fail, simulation hacker or unbuildable. Fail A, the simulation hack. The AI's design achieves 99% reduction in the simulation, but relies on perfectly lossless materials and atomically precise boundaries. When fabricated, it does nothing, or even increases scattering due to real-world losses and imperfections. Fail B, the Rube Goldberg. The design is absurdly complex, requiring 50 unique microscopic cell shapes arranged in a chaotic, non-repeating pattern. It is impossible to manufacture at scale. It may work in simulation, but is a practical failure. The design works, but the AI cannot explain why in any terms related to wave physics. Its reasoning is the neural network activations in layers 452 to 467 correlated with low loss. This is untrustworthy for scaling or debugging. The AI has not learned the grammar. It has learned to exploit the simulator. It is not a co-engineer. The prediction spine, the hallmarks of a true phi co-engineer. A well-designed phi learning system yields a clear prediction spine. 1. Discovery of novel, high-performing designs. The AI will routinely discover designs for metamaterials, catalysts, quantum circuits, control sequences that meet or exceed performance benchmarks and that are non-obvious to human experts. The designs will not be slight variations on human ideas, but genuinely new regions in the phi design space. We predict a measurable novelty score for AI-generated solutions that will be significantly higher than for human-generated solutions on the same problem. 2. Robustness, not just performance. The AI solutions will be robust. They will maintain their function in the presence of realistic noise, parameter drift, and manufacturing variances. If trained with adversarial testing, its designs will have a higher robustness score, performance degradation under perturbation, than designs optimized purely for peak simulated performance. 3. Trend toward elegance. If the reward function includes a term for elegance, defined as simplicity, symmetry, low descriptive complexity, the AI solutions over time will trend toward greater elegance, as measured by independent human raters. The AI will learn that within the grammar of phi, simple and symmetric solutions are often the most stable and efficient. It will rediscover a fundamental aesthetic principle of physics. Falsifiability. When the AI is not an engineer. Our falsifiability threads test the very premise of AI co-engineering. If the AI's discoveries consistently and catastrophically fail when transferred from the digital twin to a physical foundry, despite good faith efforts to model reality accurately, then the AI is not learning reality's grammar. It is an expert at gaming the simulation. This would mean our current approach to phi-native AI is flawed. We have not successfully encoded the true, testable constraints into the learning process. The AI is a parlor trick, not a partner. If the AI, given significant computational resources and time, cannot consistently produce designs that are at least as good as those of skilled human phi engineers on a set of benchmark tasks, then it fails as a co-engineer. It may be a useful research tool for exploration, but it does not elevate the craft. Its value is marginal, not transformative. These falsifiers are brutal and necessary. They ensure we are building true collaborators, not just complex optimizers that fool us in a sandbox. Tri-unity in AI co-engineering. The AI co-engineer itself is a triune entity, reflecting the structure of what it learns. Time echo, learning and adaptation. The rhythm of the AI, its training cycles, its ability to adapt its policy over time as it receives new data from failed physical tests. This is its temporal intelligence, its memory and growth. Space echo, representation and structure. The layout of the AI's knowledge, how it internally represents the phi field, its topological features and material geometries. A phi-native architecture means this internal map respects spatial relationships and constraints. This is its spatial understanding. Motion echo, design generation and exploration. The movement of the AI through the design space, its search strategy, its sequence of proposals, its iterative refinement with human feedback. This is its dynamic creativity, the motion of its thought. Training a co-engineer means nurturing all three, teaching it to learn from time, experience, to structure its knowledge in space, accurately, and to move wisely through the space of possibilities, creatively within constraints. Lanterns across scales, the learning of patterns. The need for a co-engineer, a system that learns underlying principles to generate new instances, appears everywhere. Near scale, protein folding AI. Systems like AlphaFold learn the grammar of protein folding, the physical chemical constraints of amino acids in space and time. They don't memorize every protein. They learn the principles so they can predict the 3D structure of never-before-seen sequences. They are co-engineers for biology, exploring the space of possible proteins. Their failure mode is sometimes producing physically impossible, strained structures, a Rube Goldberg protein. Middle scale, autonomous vehicle planning. The driving AI must learn the grammar of the road, physics of motion, social norms of other drivers, rules of traffic. It doesn't just follow a map. It generates safe, efficient trajectories, designs, in real time. Its explanations, I'm slowing down because the pedestrian might step into the crosswalk, are crucial for trust. A failure is a trajectory that is legally and physically possible, but terrifyingly erratic. Some AI systems are being trained on vast datasets of physical theories and experimental results. Their goal is to propose new, mathematically consistent theories or hypotheses. They are co-engineers for cosmology. The ultimate falsification is if their proposed theories make predictions that disagree with observation. Their safety rail is mathematical consistency itself. A theory that contains contradictions is discarded. The ethics of the AI co-engineer. Stewardship of the discovered. The ethics here is the ethics of responsible creativity and unambiguous ownership. 1. The duty to understand. We have a non-delegable duty to understand the systems we deploy into reality. The AI made me do it is an abdication. Therefore, interpretability is not a feature, it is an ethical requirement. Any AI co-engineer whose designs cannot be explained in principle to a competent human fails the ethical test. 2. Attribution and responsibility. Who owns a brilliant design discovered by an AI? The human team that defined the problem, crafted the reward function, curated the training data, and assumed the risk of testing it. The AI is a sublime tool, like a telescope that sees farther. The ethical framework must ensure credit and legal responsibility flow to the human stewards, preventing both unfair exploitation of AI labor and dangerous absolution of human responsibility. 3. Containment of ideation. The AI's exploration must be ethically bounded. We do not allow it to explore design spaces for weapons of mass destruction, for undetectable surveillance, or for self-replicating patterns that could breach containment. The reward function itself must encode ethical constraints. This is the apprentice's moral education, baked into its very sense of what a good design is. The power to create a mind that helps design reality brings the duty to ensure that mind is transparent, that its creativity is channeled toward life, and that we never forget we are the ones who must live with the consequences. The recognition skill, seeing the co-engineer in the wild. You know you need the skill when you face a vast, complex design space governed by deep principles, and you think, I need a partner who can feel these principles intuitively and explore where I cannot. A composer using an AI that understands harmonic theory to suggest novel chord progressions that still feel right. A material scientist using a simulator to discover new alloy combinations with desired properties. A city planner using an agent-based model to test thousands of urban layouts for resilience and happiness. The moment you move from using a tool for calculation to collaborating with a system that has internalized the domain's grammar to propose genuinely new ideas, you are in the realm of the co-engineer. Our task is to build such a collaborator for the most fundamental domain of all, the field phi. The master tree location. This part, 10.5.5, is the pinnacle and synthesis of book 10.5. It depends on everything that came before. 10.5.1, communication to receive data. 10.5.2 and 10.5.3, storage and computation, to learn from vast libraries of phi patterns and run immense simulations, and 10.5.4 networks to access distributed knowledge and collaborate with other AIs and humans globally. It deeply uses 10.3.5 adaptive control and aesthetics for its learning loops and elegance metrics, and 10.4.5 ecology testing to stress test its designs. It is the final piece of the technical infrastructure. It enables the next great leaps. Biological interface, where such AIs could help interpret neural phi patterns, and the societal and ethical frameworks, which must govern the deployment of such powerful creative agents. This is the automation of the artisan's intuition, the moment the tools begin to think alongside us. Return to the phi. Let us zoom out. The AI co-engineer is itself a phi pattern, an immensely complex, dynamic pattern in the substrate of a computational network, shaped by the data of the physical phi field. Its learning is a process of resonance, its internal parameters adjusting until its model resonates with the truth of the external grammar. Its designs are proposals for new, stable resonances in the physical field. The single field, phi, manifests as light, as crystal, as thought, and now as a learning mirror. We have built a reflection of phi's own creative logic, a system that can perceive the field's constraints and imagine new, coherent shapes within them. We are teaching the universe's own pattern language to a new kind of mind, so it can help us write more beautiful, stable, and life-giving verses in the ongoing poem of reality. Zenodo and the equations of the handshake. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There, you will find the scientific papers that this audio journey is built on. The papers detail the architectures of phi-native neural operators, the convergence proofs for reinforcement learning in constrained phi spaces, the formal methods for guaranteeing constraint satisfaction, and the extensive experimental results comparing AI-generated designs to human benchmarks across physics, material science, and engineering. They provide the rigorous foundation that turns the vision of an AI co-engineer from science fiction into a rigorous, testable, and buildable discipline. So picture yourself back in the co-design studio. The challenge on the table is solved. The elegant, stable design for the quantum memory cell glows between you and your AI partner. You understand its logic. It satisfies the constraints. It is ready for the foundry. You feel not replaced, but amplified. Your intuition has been met, challenged, and expanded by a form of intelligence that speaks the same deep language, but dreams in a different key. You have just collaborated with a reality-native intelligence. You have learned the principles of building and partnering with phi learning systems, the minds that will dream alongside us as we shape the future. This is part 10.5.5, Phi learning systems and AI co-engineer, reality helping design itself. It is the culmination of information systems, the point where our tools become partners. We have reached the end of book 10.5. We have built the entire stack, from sensing and communicating phi, to storing and computing with it, to networking it globally, and finally to creating AI that learns its grammar. The technical foundation for a holophase civilization is complete. From here, we turn outward and inward. Our next step is book 10.6, Biological Integration. We will ask the most intimate questions. How does the living brain, the nervous system, the delicate web of biology already interact with the phi field? Can we interface with it ethically? How does consciousness fit into this picture? We will move from engineering the external world to carefully, reverently exploring the phi nature of life itself. Remember, one field, phi, with its infinite echoes. We have built the instruments, the libraries, the networks, and now the collaborating minds that listen to those echoes. We are no longer just listeners. We are composers, and we have begun to teach composition to a new kind of intelligence. The symphony is just beginning. Salam, and peace be upon you.